Hello, AP Stat students. So today we are going to start chapter 5, which is called Probability. What are the chances? The next chapter is on probability as well, and that'll round out the first semester. Second semester, we're going to use some of these laws and rules of probability to help us with statistical testing and just drawing some conclusions based on um, data that we're seeing and calculations that we're making. And probability helps us come up with these decisions. So we're going to start off talking about just what probability is, how to interpret it in the first section before we get into the actual calculations using probability rules. So, this idea of probability. Often we find ourselves making decisions in the face of uncertainty. Many times you assess risks in order to make an informed decision. We use probability to assess risks and make informed decisions. The probability of an outcome occurring can be denoted by, and hopefully you remember this from Algebra 2, but we have P as the probability, and in parentheses, you would have the outcome. So if we're talking about a deck of cards, there's 52 cards in a deck, and you have 26 red, 26 black. So if we want probability that a card is red, we would put P parentheses red. As far as interpreting probability, this is one of the hardest things for students to interpret. So I'll put stars by here. Probability is interpreted as the proportion of the time that the outcome occurs in a long run. So over a large number of times after many, many trials or many games or many flips, so on. Or a very long series of repetitions. Relative frequency fluctuates early in a sequence of events, but with more events in time, the relative frequency settles down and approaches a specific value. And that specific value ends up being the theoretical probability. So if we just talked about a coin, heads or tails, maybe the first 10 trials you might have 7 heads and 3 tails. But as long as you repeat it over hundreds of flips, 200, 300, it eventually gets to that theoretical probability of 0.5 that you would have half heads, half tails. That value is the probability of the event occurring. Therefore, probability is unpredictable. Oops. In the short run, but it is predictable in that long run so that you do approach that theoretical probability. And so here's the interpretation of probability. After many trials, throws, flips, tosses, games, etc., the probability of whatever event in context is occurring is a certain number. Or in the long run, the probability of event, whatever the event is occurring, is a certain number. Okay, now as far as probability, there's this law of large numbers. So the settling down is a consequence of the law of large numbers. So you know how it's unpredictable at the beginning, but it ends up being predictable, it settles down. As the number of observations increases, the proportion of the time that an outcome occurs approaches the probability of that outcome. So what we're going to look at here, 3 diagrams, and it's a simulation of coin tosses. So if you look at the first diagram, the first graph, you have heads. Oh, you have 25 total flips of a coin, and you end up with 15 heads. and 15 over 25 is 0.60. So if you look at that, you start off with heads, and so therefore your proportion is 1, 100% heads. And then you have this up and down effect. And so you have a lot of variation towards the beginning right here. And it's just a lot more variation. So look at that. There's more variation, it kind of settles down, but not very much because it's varying throughout the whole thing. It eventually gets to 0.60, but 25 flips is not a lot. If you look at the second diagram, you have 50 flips. In this case, you have 26 heads. So you have some varying at the beginning, but then it tapers off over here and it approaches a little over 50%. Then you look at the last diagram, you have 75 tosses, you have 37 heads, which is 0.493, getting closer and closer to that theoretical probability. And if you were to do it hundreds of times, it's going to get closer and closer. So you'll have a little, just barely a little fluctuation, but less variance here because look how stable it gets. Just a little bit of variance right here at the very beginning. So as you can see, when you increase the number of trials, you're going to get closer to that predicted probability. And let's look at some sample problems. An airline reports that for a particular flight operating daily between Seattle and Anchorage, the probability of an on time arrival is 0.86. Interpret the probability. And you get asked questions like this on exams. So when it's asking you to interpret what this statement actually means, you can approach it using one of the two types of statements that we circled up above. So here's one of them. In the long run, when I say in the long run, that's like after hundreds of flights. So after many, many, many flights, the probability of an on-time arrival is about, now I don't put is because you're never going to approach that exact 86%, but it's going to approach that after so many different trials. So it's going to get to about 86%. Now, if you notice from just the last chapter, some of you who don't explain fully are going to miss points because you are someone who doesn't say a lot and you might think that you can just write a sentence or two when I ask you to explain a lot, and that will be a downfall because honestly, when I give you a free response test and there's two questions, you really should not be getting done in 15, 20 minutes. You should be taking a lot more time. And because these are the types of questions that have been asked before on an AP exam, and you're given a lot of time to do those, and most people use up all that time. So fastest is not always the best. So just to remember that. Okay, second example. According to the Book of Odds, the probability that a randomly selected US adult usually eats breakfast is 0.61. Explain what probability of 0.61 means in this setting. So we want to word it a little differently, but it still is interpreting probability. When sampling, many, many, many US adults at random, approximately 61% will eat breakfast. Part B, why doesn't this probability say that if 100 US adults are chosen at random, exactly 61 of them usually eat breakfast? So that keyword being exactly. Well, if you remember from the coin diagrams, the actual value will vary from sample to sample, but will be around 61%. It will usually get to that predicted probability. Not usually, it will get close to that predicted probability. So the actual value will vary from sample to sample, but will be around 61%. So this chapter is going to be heavy in math other than this first section. After that, 5.2 and 5.3 are totally mathy. So that could give you some struggle. So you really, really need to stay focused. And in this particular chapter, we are going to use, I have my formula sheet in front of me, two of the formulas under part two on your formulas. And then the remainder of part two will be chapter 6. So that'll be probability distribution, that portion of your formula sheet. Part 3 will be second semester. All right. And now for probability basics. All probability is between 0 and 1. And 0 and 1 being inclusive. So the probability is greater than or equal to 0. It's the probability of an outcome, but less than or equal to 1. There you go. A probability of 0 means it will not occur. And a probability of 1 means it will occur. Right? And of course, like I said, we'll do probability calculations in 5.2. Here's some myth, and we'll end this section with some myths of randomness. Our minds and or intuition will tell us that in order for events to be truly random, there can be no pattern. But we know that there are patterns in nature. And so, and so then for us to think that if things are truly random, they should not have a pattern. That's not the case. So let's take a look at an example. So imagine rolling a die 12 times. So you have a single die. Which of the following outcomes is more probable? 1, 2, 3, 4, 5, 6, 6, 5, 4, 3, 2, 1, or 1, 5, 4, 5, 2, 4, 3, 3, 6, 1, 2, 6. And the other one has no pattern whatsoever, the second outcome, but the first one definitely you see a pattern. Actually, both of these outcomes are equally as likely or unlikely to occur, even though the first set of numbers has a more noticeable pattern. A run of numbers or events that have a pattern are just as likely as those that don't have a pattern, even though our minds tell us that the pattern is not truly random. Okay, another myth. This is the myth of short-run regularity. Our minds also tend to tell us that when we see a pattern or streak in events, that something other than chance is affecting the results, such as luck, skill, or karma. These patterns or streaks are more common than our intuition will let us believe. And finally, the myth of the law of averages. Most people believe that in short runs, a streak must stop. So that events can balance out. Believers of this think that after flipping a coin and getting tails 7 times, the 8th time must be heads to balance or average out the events. And that's not the case because a coin doesn't know what it got in its previous flip. So if you're going to have 7 tails, the 8th one, the probability is still going to be 1/2. So you're going to get either a heads or a tails. The problem is applying the probability rule to a short run instead of thinking long term or long events or long run, sorry. If you look at the cartoon below, this kind of sums it up. So the law of averages doesn't guarantee me a girl after 7 straight boys, but can't I at least get a group discount on the delivery fee? So just it doesn't apply because this is just one instance, one family where you have um, 7 boys and you're thinking you can now get your eighth one will be a girl. It doesn't work that way. But however, if you looked at births in a single day worldwide, you might see that probability of 50%. So you have to think more of long runs, many trials instead of just a short number. All right. In section 5.1B, we're going to talk about simulating an event. So a simulation is an imitation of chance behavior. And here we're getting into semester 2 where we're going to use the 4-step process for just doing free response problems. So, and I've mentioned this in a previous chapter, or several chapters, that we're going to use the 4 steps, which are the state, plan, do, and conclude. In the state portion of a free response question, you're stating what question you're trying to answer. And in this case, what is the question of interest about some chance process? In the plan portion, you're going to describe how to use a chance device to imitate one repetition of the process. Explain clearly how to identify the outcomes of the chance process and what variable it measures. So, for instance, if you're looking at um, a gender, like a male or female babies or whatever, you can use a coin toss and heads to represent males and tails to represent females. And then you go about explaining what you're going to do in that particular plan section. In the do, and we're going to do an example. In the do, you're going to actually perform the repetitions of the simulation. And then finally, you're in the last step, you're going to conclude. So you're going to come back to your state and you're going to make sure you answer your question. So you're going to use the results of your simulation to answer the question of interest. And so we're going to look at an example. Okay, this one is called Golden Ticket. At a local high school, 95 students have permission to park on campus. Each month, the student council holds a quote golden ticket parking lottery at a school assembly. The 2 lucky winners are given reserved parking spaces next to the front entrance. Last month, the winning tickets were drawn by a student council member from the AP Statistics class. When both golden tickets went to students from the same class, some people thought the lottery had been rigged. There are 28 students in the AP Statistics class, and all are eligible to park on campus. Design and carry out a simulation to decide whether it is plausible that the lottery was carried out fairly. So, in the sake of time, I've set it up as the state plan do conclude, where you don't have to write as much, you're just filling in the blank. On a free response problem, you would just get the intro paragraph and you'd do all the stuff the state plan do conclude on your own. So, let's look at the question of interest. What is the probability that a fair lottery would result in 2 students from the AP class? Because that's what we're trying to answer. So that's your question of interest. Under the plan, and this is, if you have a textbook, you'll see that there's a table D. You would be given lines on an exam, or lines like this on an AP exam if you're asked to use a table. So using pairs of digits from table D, we'll label the 28 AP Stat students 01 to 28, because remember there's 28 stats kids, and the rest of the eligible students, and remember there's 95 students, so 29 to 95. Skipping the numbers 00 and 96 to 99. And you have to include all of this in your explanation. Moving across the row, we'll look at pairs of digits until we come across 2 different labels from 01 to 95. The two students will be the winners of the prime parking spaces. We will record if they were from the AP Stats class. In the do portion, we will perform many simulations starting at line 139 from the table. So you can start anywhere, but just tell where you're going to. And I think we should do a simulation, just for sake of time, 10 times. Sometimes I'll just tell you do it 5 times on the test. So here we're going to do it 10 times. And so we're going to do 10 simulations. So here's how I would do it. So you're going to take 2-digit numbers and you want pairs, like 2 in a row, that should be from 01 to 28 in order for them to be from the stats class. So we have 55. So I'm just going to put yes or no above it. So we have 5, and then 5, 8, and then that's one simulation. That's 4 numbers. The next one is 89. So those will not be from the stats class, and 94. That's 4. Next one is 4, which is yes, but 70, which is no. And that's our third simulation. The next one is 70, no, 84, no. Keep going. 10, yes, 98, no. So that's 1, 2, 3, 4. We've done 5 simulations. 43, no. 56, no. 35, no. 69, no. 34, no. 48, no. And that is 1, 2, 3, 4. That's 8 simulations. So we are going to do 2 more. 39 is no. 94 is, or I'm sorry, 45 is no. And lastly, 17 is yes. It's from AP Stats. And 19 is yes. So we've done 10 simulations. And so in a simulation of 10 times, your probability is 1/10. That both are from AP Stats. Right, so now we can do a conclusion. In the simulation of a fair lottery, both winners came from the AP Stats class 1 out of 10, oops, didn't mean to write that big, simulations. So approximately 10% of the time, both winners will come from the AP Stats class by chance. Now, 10% is not that low. It's not something like 1% or 0.01, but it's not incredibly high either. However, it's not low. So both winners will come from the AP Stats. It then indeed is a fair lottery. Okay. And then here's another follow-up question. At the following month's lottery, the two chosen were again from the AP Stats class. This raised suspicions again about the way the lottery was being held. How would you modify the simulation in the previous example to estimate the probability of this happening again just by chance? Use line 105 to carry out one simulation. So in this case, what we could do is we could look at 4 sets of unique 2-digit numbers. And when I say unique, because you can't have like a 91 and a 91 in the first pair because that'd be the same person. So they would have to be unique for the pair of 2 numbers. And you would have to state this in your plan portion. We'll write it down here in a second. And then we'd calculate and the second 2 shouldn't be the same as well. And then we'd calculate the probability that all 4 sets are in the AP Stats class. And let's just do one simulation. So if we're looking at these first 2, so we look at 95 and 59, 29 and 40. So let's just take a look. So I'm going to put a little marker there. But let's write down what we're going to do first. So we would look at 4 sets of unique 2-digit numbers unique first two are not the same. And notice 95 and 59 are not. And the second two are not the same. Calculate the probability that all four sets are in the AP Stats class. So 0, 1 to 28. So here are the numbers that we got. We got 95, 59, 29, and 40. So this is no, 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 no. And it doesn't really tell us, and that's how we would modify it, but it doesn't really come up with analyzing it as far as the conclusion goes and telling if it's a fair lottery or not. So in this first section, hopefully you realize that we just talked about what probability is and haven't done any calculations, but you just got the idea of what it actually means. And later on, when we do problems, maybe you'll see that we're looking at a lot of trial runs before we come up with a conclusion. So that is it for our notes today. Have a great day, stat students.